If a large horizontal disk is rotating with an angular speed of 1.5 radians per second and has at that instant an angular acceleration of 3 radians per second squared, what is the total acceleration of an ant sitting on the disk at a point 80 centimeters from the center of the disk? So maybe we can imagine that this is the disk, and I didn't really say if the ant was sitting on the edge or anything, right? So maybe I could just draw in an ant here somewhere and say, okay, here's this little tiny ant. I'm going to try to give it some legs or something. How many legs do insects have again? Anyway, hopefully I got that right. So anyway, there's that ant. But I think the thing I would look at is to find the total acceleration, I need to recognize that it's going to have centripetal acceleration because it's on a rotating thing, right? So there would be centripetal acceleration. But it doesn't really, let's see. Well, it doesn't really say if it's speeding up or slowing down, but it does say it has, at the instant that we're interested in, an angular acceleration of 3 radians per second squared. And so maybe I can just interpret that and say, okay, therefore the ant must also have a tangential acceleration related to that. So let me draw a bigger picture of those two accelerations I just drew for the ant there. I mean, they're super small right there, right? So we're talking about a centripetal that I kind of drew down and somewhat horizontally looking. I drew this tangential acceleration, and what I think should happen here is that the total acceleration should be the sum of these two. In other words, if I were to take, like, one way of looking at, like, why did I draw what I just did, is if I were to take this centripetal acceleration vector and just move it so I'm doing head to tail vector addition, then, hang on a second, let me get that just right. Okay, then, and let me also move this label here so it makes sense. Then the total acceleration really is just the sum of those two head to tail. But since these two, I think, are at right angle, right? Because tangential acceleration is tangential to the kind of rotational circular motion the ant is doing, and centripetal is always towards the center, so it makes sense that those would be at right angles. So that means that let me switch to pen again. The total acceleration should be the sum in quadrature of these two components. So, okay, can I find what these two are, right? The tangential acceleration is equal to the radius times the angular acceleration, and the radius is, I'm going to turn this into 0.8 meters. That's that 80 centimeters, right? Because it's saying that the ant is sitting at the disk, at a point 80 centimeters from the center, but I'm regarding that as the radius at which the ant is located relative to the center. And then the angular acceleration is 3 radians per second squared, or just per second squared, I guess, right, since we want to get meters per second squared. And then I might go get a little calculator help and see that that is equal to 2.4 meters per second squared. And we also have the formula for the centripetal acceleration, which is, maybe in this case, since I'm given an omega there, I'm going to use the omega squared r formula for that. And omega in this case is that 1.5 radians per second that we were given. So that's going to be 1.5 just inverse seconds in the formula squared times 0.8 meters. And I think it makes sense that this will give me something in meters per second squared. I run that into my calculator and I get 1.8 meter per second squared. And then based on this formula here, what I'm going to calculate for the total acceleration will be 2.4 meters per second squared. And oops, I had this radical thing kind of dipping down there too much. All right, plus 1.8 meter per second squared, and squared the whole thing. Okay, but my calculator does short work of that and gets me the nice simple answer of 3. Isn't that remarkable that that turned out just to be 3 meters per second squared? Maybe I should have made it 3.0 meters per second squared to get the sig figs correct, but there's the answer, so it checks out.